such that a to the d is not equal to 1 mod n, and a to the 2rd is not equal to n minus 1 mod n, then you know it is composite. So if these are both true, then it is certainly composite. It is not prime. So the random version of this is you start picking A's out of the hat within a certain range, and at some point, if they all seem to be, if one of these two conditions is true, you say, well, it's probably prime. The deterministic version is that you use all the A's in a certain range, and I forget what it is, but all the A's up to a certain range, and if they all follow this condition, then, wait a minute, and, no, there we go, all right. If one of these is true for every A, and you go through a whole range of A's that are available, then it is certainly prime. Since these may be very large numbers, you have to do a lot of multiplications before you can do the modulo. And it would be nice to do those multiplications in an efficient way, and the Montgomery algorithm does that. So an example that was used was, let's say ask if 221 is prime. Is it? Well, let's find out. So, of course, n minus 1 is 220, so n minus 1 is equal to 220, which is 2 to the 2 squared times 55. So, let's proceed to compute a couple of things. A to the d then, mod n, oh, we need an A. So we're going to choose an A of 174. No reason. So we have 174 to the 55 mod 221 is equal to 47. Okay, that's not equal to 1, so now let's do 2 to the 2 to the d mod n, which is 174 to the 110th mod 221, which is equal to 220, it turns out, which is n minus 1. And so if either of these is true, then we cannot, we haven't proven it's prime, but we haven't proven it's not prime. So the terminology that's used apparently is either the 221 is either prime, or 174 is a strong liar for the fact.
So now you choose another number at random, and
what you'll find is if you choose the correct number, let's say A equals 137, that both of these conditions are true and that it is therefore composite. It does not tell you what the factors are, however. 13 and 17. Did you figure that out? Okay, cool. So it does not tell you what the factors are, it just tells you that there are factors. So finding out what the factors are is still hard. But at least you know it's not pointless. So it'd be interesting to implement this. See how fast you can do it. And maybe it's used as part of an RSA algorithm. So you could implement an RSA encoder. I don't know quite how much to do on the topic. I can read about it. You can read about it. I might be able to read it faster, but maybe not. So I'll talk more about it if you want, but you got to tell me what you want to hear about. Yeah, I'll do some other topics too, but I think that this is probably more interesting than doing a sieve, and probably a lot faster because it's got a lower order of algorithmic complexity, and it doesn't require an enormous number of disk accesses for large numbers, which it would kill, or some sort of solid state memory would probably kill performance. Any questions? Maybe interested? Large primes as an art form? So what I thought I'd do, rather than beat primes to death, is talk about a little bit about image filtering, which is probably of use in several projects, including eye tracking and maybe card recognition, some other things. And there's a fairly general scheme for doing image filtering, which parallelizes very well on a FPGA. And that is a so-called convolution filter. So if you have a two-dimensional array of pixels representing some image, then a convolution filter, let's say we want to filter some pixel xy, so this guy right here. Let's say we want to smooth the image. We want to get rid of impulse-like noise in the image. We want to, in other words, blur it slightly. We want to come up with a filter that is local, that uses information about the pixels around this pixel. But locality can be fairly large. It could be several pixels by several pixels. But for right now, I'm just going to talk about 3x3 convolution filters that use information from the 9 nearest neighbors to come up with a modified value for a pixel. And generally what you're going to do is take every pixel in that 3 by 3 region, multiply it by some constant of your choice, multiply the intensity by some constant of your choice, and then assign the sum of all those products to the output image. So you're going to assign that to that pixel, move this template over one pixel, do the calculation again. So you're going to do a 9 by 9, a 3 by 3 multiply and add, so a 9-term add for each pixel. If you go a 5 by 5 template, you're going to do 25 adds per pixel. But if you keep the proper shaped buffer, you can do this at video rate. You don't have, there's no overhead on the FPGA. At 640 by 480 resolution, you have plenty of time to do one convolution operation, one 3 by 3 convolution operation for every pixel that is submitted to the VGA in real time. We'll talk about that in a minute. So then, in the new frame, at point x, y, the form of the arithmetic is going to be that we're going to do a sum over j from x minus 1 to x plus 1 I, j equal y minus 1 to y plus 1 of the old pixel ij times w x minus I wait a minute. No. All right. Y minus I. This should be x minus I, y minus I. So you're doing a sum over of the 3 by 3 array of pixels around the original pixel. And so you could imagine setting all of these coefficients to 0.1. Let's point 0.11. And that would be a flat-out averaging filter, because 0.11 is about the reciprocal of, is 1/9 more or less. So if you multiplied the intensity of each of these pixels by 0.11, added them all together, you would have produced a low-pass version. It's a smoother. It takes the average of all of the pixels in the block and then applies it to this pixel. Makes the new pixel equal to the average of all the pixels around it. Is that the best low-pass filter you can come up with? No. But it's really easy to implement. But you can do an amazing number of things with the convolution filter. For instance, how would you take the spatial derivative? How would you take the first derivative in x? So I want the partial of the intensity with respect to x. So we could do -1, -1, -1, 1, 1, 1. And then divide by 3. So if we put a uniform intensity over this template, if every point on the image has the same value, 0.5, then the output into this pixel in the next image will be 0. There's no gradient. If there's a large change in this direction in intensity, the output will be positive. If there is a change in intensity in the other direction, the output will be negative. If you're using RGB images, you have to do this 3 times. One for the red channel, one for the green channel, one for the blue channel. Typically what is done, however, when doing gradients or other image processing, convolution processing, is to make an intensity which is equal to approximately 0.3 times the red channel plus 0.6 times the green channel plus 0.1 times the blue channel. This equation reflects the fact that our eyes perceive intensity mostly in the green and in the red and only very slightly in the blue. So this is a human balanced RGB intensity conversion. Approximate. There's a couple of, there's some 0.1s, 0.01s in here that I'm just ignoring because it hardly matters. So when I say intensity here, I mean this function of the red, green, and blue image converted from a 3-space to a intensity. So we can do partial of intensity with respect to y by using a convolution filter that looks like this: 1, 1, 1, 0, 0, 0, minus 1, minus 1, minus 1. These are not the only possibilities. This is just an easy possibility. This particular form of the spatial derivative is called a Prewitt filter. Prewitt filter. Presumably that's somebody's name, because otherwise it makes no sense to me. It's not Prewitt as opposed to Postwitt. It's a name. So we can find strong gradients by using some combination of this operator and this operator, perhaps applied one after the other, which suggests that it might be useful for an edge detector. So you might be able to find, say, if you're looking at an eyeball here, you might be able to detect the edge of the iris and the edge of the pupil by changes in intensity. So you might be able to detect the various crossings here. But this does bring up a question of what do we mean by an edge in an image? High spatial frequency. That's a rather sophisticated answer. Yes, you're quite right. So there's a so that there is a sharp change in the intensity, right? That if we have some space direction, say x or y here, and intensity, that there is some fairly sharp change in the intensity, which when you Fourier transform it in space rather than time, results in a high spatial frequency. So that says that one way of detecting it would be to look for a sharp change, a change in intensity that's above some threshold, for instance. But what about noise? Images always have noise in them. Particularly cheap CMOS cameras have lots of gain noise, and so pixels that are next to each other and should be the same intensity because you're looking at the same color thing aren't always the same intensity. And so when you take a derivative of those, when you're going to take the spatial derivative of that, you'll get a non-zero gradient where you expect to get a zero gradient. So certainly detecting a threshold is a good idea. There's other ways, though, of detecting thresholds, and we'll talk about that. Talk about edge detection a little bit in a more complicated context. One way of enhancing the finding of edges is to say not only is it a strong gradient, but it's connected in a direction perpendicular to the gradient. So the region where the gradient is high is continuous perpendicular to the gradient. Remember can you all define a gradient? Gradient operator. The gradient is a vector quantity of a scalar field. It's a vector derivative of a scalar field. So if you, in this case with the eyeball, the gradient, let's say that this area is white out here, and then we have a fairly dark iris and a black pupil, and most people's pupils are black because the light goes in and doesn't come back out because it's being detected. But irises are quite different in color for reasons that are obscure, but may have to do with reflected sunlight off of ambient. But certainly there's a strong gradient in the direction of, if we do an arrow in the direction of the positive gradient, there's a gradient in intensity like this, whose length of the vector being the contrast between dark and light, and the direction of the vector being perpendicular to the boundary between them. And some algorithms use continuous continuity in the direction of the gradient to determine valid edges versus bogus edges versus noise edges. Convolution filters are not the only kind of filters that exist. Let's say that you have an image of some nice circle, low contrast, kind of a gray circle on a white background, and your detector gets struck by a cosmic ray while you're taking the picture. Then you'll have a bright white, you'll have an extremely bright white dot on the image corresponding to a high energy strike. And if you use any kind of convolution filter on that, you'll still have a white dot there, unless you smooth it so much that the edges of this gray region become smeared and everything becomes smeared. For cases where you have true impulse noise resulting from processes that are extreme, like cosmic ray strikes, it is better to use a median filter and take the median of, say, 9 pixels rather than the mean. It's because the median will always ignore outliers. It'll always ignore extreme events. However, it is harder to characterize because it is not linear. A median filter is not a linear filter. And so the performance of it has to be carefully validated for a class of images whenever you use it. It also tends to be harder to calculate because you have to order a group of items to find the median. But that's just to say, even though convolution filters are used everywhere for everything, they're not the only kind of filters that exist. Quite often for an image recognition scheme, either for eyes or cards or whatever, the very first operation will be to put a smoothing convolution filter on the image to get rid of high frequency noise, to get rid of minor variations in the background. And what is often used instead of a simple averaging filter is an approximation of a Gaussian. So the center will be high, the four sides will be lower weights than the center, and the corners will be lower yet than the edges. And that will tend to concentrate the energy. It tends to not alias, for instance, and gives sort of what I guess you might call an optimal blur. It gives you kind of the best degradation of the image you could hope for in some local sense. I'll talk more about this next time. And how to parallelize it and how to go about doing some more operations with it. But anybody, let's see, two people are going to be using image processing probably. Who else? Okay. All right, we'll continue on this on Friday. Any last minute questions on Lab 4? Any questions on the final project? Comments on final project? So 1 week from now, you start, 1 week from Saturday, you start the final project. So, got to get it tied down pretty soon. Okay.